All right, we've done design of concrete beams where we know the dimensions. So the only thing we have to design are is the steel itself. Now, what if we don't know the dimensions? Again, concrete can be any shape you want to pour it in, unlike steel. So that gives you more freedom, but it also means you can't just look things up in a table. So what we're going to do is we're going to start out with a reinforcement ratio. If you recall, the reinforcement ratio is the area of steel divided by your beam width and your depth to your tensile reinforcement, which is basically your effective area of concrete. We're going to say, let's have a reinforcement ratio about equal to beta 1 F prime C for Fy. This is going to be our target reinforcement ratio. And I wrote that in red because target is awesome. So, if we have an F prime C of 4,000 psi and an Fy of 60 ksi, then our target reinforcement ratio is about equal to 0.85. That's my beta 1 for 4,000 psi, 4 ksi concrete, 460 ksi steel, obviously the 4s kind of drop out, but so 0.014 is what we're going to aim for. We obviously still don't know our area of steel or our B or our D, but now we have an estimated ratio that we want to come up with. So we're going to use a couple rules of thumb. We're going to start with our overall dimensions, and we're going to use some rules of thumb. So we're going to estimate our height is going to be between the clear span over 18 or this clear span over 12. Ln is clear span, longitudinal span. Right, the length, basically. And we already said earlier that we can guess D based off of the height. So D is equal to H minus 2.5 for one layer of reinforcement. Of tensile reinforcement, right? Or H minus 3.5 inches. I should make sure to use units. If you have 2 layers of tensile reinforcement. Right, that allows for your clearance, your cover, your stirrup or tie, and then half a bar diameter, basically. Longitudinal bar diameter. And then we're going to have a ratio of our width to our height. About equal to 1/3 to 1/2, right? If it's 10 inches wide, it'll be 20 to 30 inches deep. We really don't want something long and squat, right? That'd be a slab. We want something tall and skinnier. So, as a note, these are just general rules of thumb. You probably have some other constraints by the architect, or maybe keeping things consistent. Your width of your column that supports the beam. You don't want to make a beam that's wider than your column. You probably want to make it about the same. I mean, I guess it could be wider, but you know. Easier to form if things are the same width, right? And your depth wise, you might need to keep it shallower for some overhead clearances. So those are the rules of thumb, and then just some other things you might have to think about. I'm sure there are a multitude of other things. So let's talk about the design process when we don't know the dimensions. Let's see. We need to calculate our required strength, our factored moment, right? Unless they're given, select material properties. estimate a reinforcement ratio. That was our equation that we just used earlier. Beta 1 F prime C over 4 Fy. Now we're going to use our design equation. So we're going to assume tension control, right? I'll assume steel has yielded. And tension control. Oh. Actually, we're just going to assume tension control, because that gives us both the phi and the stress in our steel. Equations. So we have our two equations, right? We have equilibrium, where my area of steel times my yield stress is equal to 0.85 F prime C AB. And I know that my reinforcement ratio is equal to AS over BD. If I solve that for AS equals rho BD. If I put that in here for, oops, right, for AS, rho BD is equal to 0.85 F prime C AB. B, go away. Now this rho, that reinforcement ratio, is the one that we estimated based off of our material properties. So the only thing we don't know in this equation, we don't know D and we don't know A, because we haven't designed anything. This is my equilibrium equation. Then I'm going to solve for A. What's that? A equals rho D I forgot Fy. Rho D Fy divided by 0.85 F prime C. And I have an equation where A and D are also involved, right? A moment. Phi Mn equals As Fy D minus A over 2. Mu must be less than phi Mn, less than or equal to. So I make this side mu over phi. That's my Mn, right? Mu over phi. I make this side, I'm going to put that rho, that equation that had rho in it, right? Rho B D times Fy times D minus this A right there minus rho D Fy divided by 2 times 0.85 F prime C. I'm going to factor out, there's two D's, right? There's this D and this D. Rho B D squared Fy 1 minus rho Fy 2 0.85 C. And what I want to get to is my ultimate goal right here is I'm going to get something times BD squared. Because earlier I said there should be a relationship between BD, well, B and H, and D is pretty similar to H. So my ultimate goal is I'm going to get mu over phi is equal to rho Fy 1 minus rho Fy over 2 times 0.85 F prime C times B D squared. I draw a little box. So I'm going to don't know B or D, but I know that their relationship needs to be about, 1 to 3 or 1 to 2-ish. And I know this prefix right here. And I know my moment and I know my phi. So I'm going to get something, BD squared is equal to something, right? I'm going to divide this mu over phi by rho Fy 1 minus rho Fy to 0.85 property. So that was number 4. Using BD squared equals something, select B, D, and H, right? Really, you're going to select B and H and estimate a D. I'm just going to keep that. Now you have known dimensions. So we're starting where we already were before. So calculate a required area of steel. Check AS min. This is what we did previously, so I'm not going to rewrite everything. Select your bars. Check fit. Right? Make sure you meet spacing requirements. And verify assumptions. Right? Which were phi, Fy. You probably estimated D off of an H that you selected. And then calculate your capacity. Make sure that it's greater than you're required. Okay. So once we get through step 5, we're back to where we were with the last lecture, and once we get to step 9, we're back where we were from the beginning of the semester. We're just adding layers of complexity, right? So let's do an example. Here we have a cantilever. We have to, right, calculate our required capacity, So let's see, we have a distributed dead load and a distributed live load. So let's calculate a factored load, 1.2 dead plus 1.6 live, 1.2 times 1 kip per foot plus 1.6 times 2 kips per foot. That should give you 44.4, not 44, 4.4 kips per foot. My maximum moment for a cantilever, right, happens at the reaction. So we're actually gonna we're gonna design something upside down, which we haven't had to do yet. Right, tension's gonna be on the top now. So my moment is 4.4 kips per foot. Here is WU times L squared over 2, right? The resultant force, the resultant load is WU times L, and it happens at L over 2 from the reaction, from the support. So WU L squared over 2. Times 10 feet over 2. Or 10 times 5. Which should give you 228 kip feet. Everybody see? So a target reinforcement ratio beta 1 F prime C over 4 Fy. So F prime C is 3000 psi. So my beta 1 is not 0.85. If we go on page 399. There we go. Beta 1. Oh wait, I'm wrong. If it's 3000, it's 0.85. Always good to double check, right? 3000, if it's under 4000, it's 0.85. So let's see. So our our target reinforcement ratio, that's a C, it looks kind of like a little, okay, is 0.85 for 3 KSI divided by 4 times 60 KSI. So we're looking at about 1%. So now I'm going to draw the section just because, all right, tension is in the top and compression is in the bottom. So I'm going to use my design equations, and I'm not going to derive that again. So if I go back and look at that equation, oh dear. Okay. I wonder if I can. Oops. Well, that's the one we went, right? I've got mu over phi is equal to rho fy 1 minus rho fy over 2 times 0.85 f prime c BD squared. And remember, I'm assuming that I'm tension controlled, so I have a phi of 0.9 and my steel has yielded. So on the left side, I've got 220 kip feet divided by 0.9. Scooch that over, I'm probably gonna run out of room. 220 kip feet. And I think I'm just gonna go ahead and put that in kip inches because probably gonna need it, right? Everything on the other side is in KSI. So a target 0.01, 60 KSI, 1 minus 0.01, 60 KSI, 2 times 0.01 times 0.01. Alright, that's my target reinforcement ratio that I just calculated. That's where I'm getting that, right? Here. Okay. Times 2 times 0.85 F times C, which is 3 KSI times BD squared. So I'm going to get 220 times 12 divided by 9. 2,933 kip inches. 101 times 60. And 0.529. And what is the units? Alright. This KSI drops out, this KSI drops out. That's good because that 1 is unitless. So this is going to be in KSI. BD squared. So I'm going to flip it, but BD squared is going to be a target. Now these are just using these equations to come up with estimates, right? 2,933 KSI, or no, kip inches. 0.529 KSI. So 2,933 divided by 0.529. 5,544 inches cubed, right? Those kips drop out. The other inches, the square inches, go up to the top. So inches cubed, which is good because BD cubed should be in inches cubed. So I'm going to use this to estimate sizes. Let's say I want a shorter beam, so I'm going to say my width is about equal to half my height, and my height is about equal to my depth. Really, you know, it's a couple inches shorter, or my depth is a couple inches shorter than my height. But, right, we're just estimating stuff. So, B is about equal to half of D. So if I use BD squared and I put that B equals half D in there, I get 1/2 B cubed is equal to 5,544 inches cubed. I get a D of 22.3 inches. which is about 2 feet. And B is supposed to be half of that. So I'm going to say my width is equal to 12 inches. Alright, a foot wide. That's generally nice, right? And if D is 22.3, H is if I assume one layer of reinforcement, my H is D plus 2.5 inches, so 22.3 inches plus 2.5 inches, 24.8 inches. Now I'm going to round that up. First of all, round up to an even number. So you wouldn't go to 25. I'm going to round it up because the longer the moment arm, the more likely you are to have your steel yielding and a higher capacity, right? More distance between them, higher capacity. You could round down to 24 and see how it goes, right? You're the designer. Because 12 and 24 sounds a lot more, nice and normal to us English units people, because that's 2 feet and 1 foot. But I'm going to round up because it gives me a little bit of extra space to get that full moment capacity. Now I'm going to re-estimate my D. With that 26 inches, right? D equals H minus 26 inches, or H minus 2.5 inches. So 26 inches minus 2.5. So that's where I'm started from last time, right? Oops. So I now have, I guess I can draw it, right? I'm going to say cantilever that's 26 inches tall. Put that at the bottom. Okay. 12 inches wide. And I need to guesstimate an area of steel, right? I remember it's going to be at the top. And I just said my D is about equal to 23.5 inches. Right. It's about equal to 23.5 inches. So my next thing, I'm going to give you guys a couple minutes to try it on your own, and then I'll work it out. Okay? If you haven't calculated, that's fine. You can pause or you can follow along. So I'm going to recalculate it with, I guess I should say with B equal to 12 inches, D equal to 23.5 inches, right? And I have my two equations. I have AS is equal to my MN, right? I have my VMN is equal to AS FY D minus A over 2. And if I solve for AS, I get AS equals MU equals VMN. There we go. I get MU divided by V, right, that'd be my MN basically. FY D minus A over 2. And then that's my equilibrium equation, and, or no, I'm sorry, that's my moment equation. My equilibrium equation is ASFY is 0.85 F prime C A B. And if I solve for A, I get ASFY divided by 0.85 F prime C B. And I can make my little chart, right, of AS and A. And I am going to start with you could use what we used last time, but a shorter version is start with AS equal to rho BD. That 0.01, right? 0.01 times 12 inches times 23.5 inches. So that means I'm starting with 2.82 inches squared. If I put that equation into, or I put that value into the equation for A, I get a value of about 5.55 inches. If I use that value of A in the first equation for AS, I get a value of 2.3 inches squared. See, it immediately came back down. If I use 2.3 inches squared in the equation for A for 4.61 inches. Oopsie, it's 2.35. Sorry. Giving away the answer here. If I use that 4.61 inches in my AS equation, I get 2.3. If I use that in my A equation, I get 4.51. And if I use that, I get 2.3 again. Now, if you had used the other method, where we, if we had used that, let me see. Where I started with estimating JD instead of estimating a row. And let's see, if I had started with an estimate of JD, AS equals MU over phi FY times JD It actually starts me off with a really nice answer already. Right. 220 kip feet, 12 inches per foot, 0.960 KSI, 0.9 times 23.5 inches. That gives me, right, 220 times 12 divided by 0.9 times 60 times 0.9 times 23.5, 2.31. So that starts me off on a better. So you could do either one, right? 2.31 inches squared. I guess that equation isn't that hard, but 2.31. So 3 KSI. Right, 4.52. I mean, we're not going to change much, right? Actually, it's 4.53. We're being technical, I guess. It's not going to matter. But if I use that in the A equation, so 2.3 inches, right? You can see it. I mean, it really hasn't changed that much. So, and then, right, I don't even know what this will probably end up with 4.51. I'm just looking at what I did on the other side. And that'll give you so there's two methods of doing it. They're basically, you're just starting at different places, and you can see how quickly it took take a couple more steps on the using rho instead of estimating the moment arm, the JD. But you get the same answer. And really, that's going to change anyway. That area of steel is just what we need, and now we have to figure out how many bars we want, right? We should probably, oh, we can check ASMin. So I'm gonna select my bars. I need about that. Let's see, if I have, if I use number 7s that have an area of steel of 0.6, am I making this up? .6. Then I would need 2.3 divided by 0.6, 3.8 bars. If I use number 8s that are 0.79 inches squared, 2.9 bars. Number 9s that are 1 inches squared, 2.3 bars, right? So let's use 3 number 8s. So let's check our fit. I'm gonna assume number 3 stirrups. Probably should have put that in. So let's see. Oh, it's in the top, but that's fine. Right. And normal cover, right? I can never make my first one look nice. Okay. So let's see. I've got my cover. My stirrups. I think I made those purple. Right. 3/8 of an inch. What color did I make them last time? Red and then green. My bend diameter. I'm sorry. DS. So 6/8 or 3/4. B is going to be equal to 2 times my cover, 1.5, not just a half, 1.5. Plus 2 times my stirrups, right, because it's on the other side. Oops, I shouldn't have, that green is wrong. That green should just go to the center here. Because I need this, right? I have my stirrups plus my inside bend diameter plus my cover, right? So I have cover on both sides. I have my stirrups on both sides. I have my inside bend diameter or radius. I keep saying the wrong one, but 2 times 3/4 of an inch. And you can get that bend diameter from the detailing in the book. Let's see. Plus, so that gives me my 2 covers, my 2 stirrups. That gets me to here on that side and here on this side, right? The center of the 2 corner bars. So I have 1 whole bar in the center plus a half bar on either side in the corner. And my diameter of a number 8 is 1 inch. And I've got 2 spaces. So if I solve for my spaces, because my B is 12 inches, my spacing between my bars is going to be about .375 or 2.38 inches. Right, because I have 12 minus 2 times 1.5 minus 2 times 3 divided by 8 minus 2 times 3 divided by 4 minus 1 plus 0.5 plus 0.5 plus 1 divided by 2, 2.38. So let's see, where did I get that? I really should put a tab on there, and I don't have one. So the inside bend diameter, somewhere around here, isn't it? There's my hooks. Oh, that was too far. It's 470. Right there. Right. I got a number 3. So the diameter is 4 dB or DS, because the B in this case, the bar in this case, is your stirrup. And I just need the radius, not the diameter, so it's 2 instead of 4. Right? Spacing. Was just prior to this, right? There it is. has to be 1 inch. Bar diameter, I've got number 8, so that's 1 inch, and let's say that one doesn't apply. So I'm okay, right? My spacing was 2.38 and it needs to be greater than 1 inch. So you're good. So we checked our fit. Now we have to calculate our nominal capacity. All right, so we selected our bars, our 3 number 8s, checked the fit. Oh, we better check AS min too. All right. Well, we're gonna do that on the next page. So, I mean, it should be fine, but you know. So if you, I just went ahead and calculated FMN. You can go ahead and do that on your own if you'd like, right? We have to calculate a new D. Why do we have to calculate a new D? Because we actually know our bar diameters. The earlier version of D was just estimating it, H minus 2.5. And it's just about H minus, right? H minus 2.5 was 23.5. So it's not that much different, but we do have to go back and recalculate it. Now that we've selected our area of steel, we have to go back and calculate the depth of the stress block associated with that to satisfy equilibrium, right? So I plug in my 3 number 8s, so 3 times 0.79 inches squared. I'm still assuming that I've yielded, which is something else that I have to go back and check. But I know my area of steel and I know my dimensions. Using that, I can calculate the depth to the neutral axis and go ahead and check that my steel did yield, which it yielded by a lot. And because it yielded so much, not only is it Fs equals Fy, but it's great enough that I'm tension controlled, so my phi is equal to 0.9 and my stress is equal to Fy. And I can go back and check, recalculate my FMN. Now I have my area of steel, my three number 8s. I have my D that I recalculated based on the actual geometry, and my depth to my stress block based on all of that. And I get a FMN of 227 kip feet, which is greater than the 220. And I'm going to add a little epilogue here. All right, I'm going to check my minimum area of steel. Maximum of, I look it up every time, 3 square root F prime C over Fy BWD, or 200 BWD. So 3 times the square root of 3,000, see I was starting to write the wrong one, PSI over 60,000 PSI, 12 inches, 23.625 inches, or 200 PSI, even though it doesn't say it, 60,000, 12 inches, 23.625. Right. 7, 8. of steel is 3 times 0.79 inches squared. I think it was 2.37. Yeah. Which is greater than AS min. So we're good there, right? 2.37 is greater than 0.95. So that is an example of from start to finish designing an entire concrete beam. Okay. That is where we'll stop. Thanks. Bye.